In July of 2022, the Texas Department of Transportation issued an emergency suspension of work on the half-finished Harbor Bridge project in Corpus Christi, citing serious design flaws that could cause the main span to collapse if construction continues. The bridge is a high-profile project and, when constructed, might briefly be the longest cable-stayed bridge in North America. It's just down the road from me, and I've been looking forward to seeing it finished for years. But it's actually not the first time this billion-dollar project has been put on hold. In a rare move, TxDOT released not only their letters to the bridge developer, publicly castigating the engineer and contractor, but also all the engineering reports with the details of the alleged design flaws. It's a situation you never want to see, especially when it's your tax dollars paying for the fight. But it is an intriguing look into the unique challenges in the design and construction of mega projects. Let's take a look at the fascinating engineering behind this colossal bridge and walk through the documents released by TxDOT to see whether the design flaws might kill the project altogether. I'm Grady, and this is Practical Engineering. In today's episode, we're talking about the new Harbor Bridge project in Corpus Christi, Texas. By the way, my new book comes out November 1st. Stay tuned to the end for a sneak preview. Corpus Christi is a medium-sized city located on the Gulf Coast of South Texas. But even though the city is well down the list of the largest metropolitan areas in the state, it has one of the fastest growing cargo ports in the entire United States. The port of Corpus Christi is now the third largest in the country by tonnage, due primarily to the enormous exports of crude oil and liquefied natural gas. But there are a couple of limitations to the port that are constraining its continued growth. One is the depth and width of the ship channel, which is currently in the process of being deepened and widened. Dredging soil from the bottom of a harbor is an engineering marvel in its own right, but we'll save that for another video. The second major limitation on the port is the Harbor Bridge. Built in 1959, this bridge carries U.S. Highway 181 over the Corpus Christi ship channel, connecting downtown to the North Shore area. When it was constructed, the Harbor Bridge was the largest project ever to be constructed by the Texas Highway Department, later known as TxDOT. It was the pinnacle of bridge engineering and construction for the time, allowing the Army Corps of Engineers to widen the channel below so that the newest supertanker ships of the time could enter the port. The Harbor Bridge fueled a new wave of economic growth in the city, and it's still an impressive structure to behold, if you don't look too closely. Now, more than 60 years later, the bridge is a relic of past engineering and past needs. The Harbor Bridge has endured a tough life above the salty Gulf Coast, and the cost to keep corrosion from the bay At.a has increased substantially year by year. The bridge also lacks pedestrian and bicycle access, meaning the only way across the ship channel is in a watercraft or a motor vehicle, which is not ideal. Finally, the bridge is a bottleneck on the size of ships that can access the port, keeping them from entering or exiting fully loaded and creating an obstacle to commerce within Corpus Christi. So, in 2011, over a decade ago now, the planning process began for a taller and wider structure. The new Harbor Bridge project includes 6.5 miles, or about 10 kilometers, of new bridge and roadway that will replace the existing Harbor Bridge over the Corpus Christi ship channel. And here's a look at how the two structures compare. The new bridge will allow larger ships into the port with its 205 feet or 62 meters of clearance above the water. The bridge is being built just a short distance inland from the existing Harbor Bridge, which is a good thing for us because the Port Authority wouldn't give us permission to cross the old bridge with a drone. It will eventually be demolished at the end of construction. The project also requires lots of roadway reconfigurations in downtown Corpus Christi that will connect the new bridge to the existing highway. The crown jewel will be the cable-stayed main span, supported by two impressive pylons on either side of the ship canal across 1,661 feet or 506 meters. The bridge will feature 3 lanes of traffic each way, plus a bicycle and pedestrian shared use path with a belvedere mid-span that will give intrepid ramblers an impressive view of Corpus Christi Bay. The project was procured as a design-build contract, awarded to a joint venture between Dragados USA and Flatiron Construction, 2 massive construction companies with a huge group of subcontractors and engineers to support the project. Design-build, or DB for those in the industry, really just means that the folks who design it and the folks who build it are on the same team and work hopefully in collaboration to deliver the final product. That's a good thing in a lot of ways, and design-build contracts on large projects often end up moving faster and being less expensive than similar jobs that follow the traditional design-bid-build model, where the owner hires an engineer to develop designs and then bids the designs out to hire a separate qualified contractor. When an engineer and contractor work together to solve problems collaboratively, you often end up with innovative approaches and project efficiencies that wouldn't be possible otherwise. You also don't have to wait for all the engineering to be finished before starting construction on the parts that are ready, so the two phases can overlap somewhat. However, as we'll see, DB contracts come with some challenges too. When the engineer and contractor are in cahoots, legally speaking, the owner of the project is no longer in the middle, and so has less control over some of the major decisions. Also, DB contracts force the engineer and contractor to make big decisions about the project very early in the design process, sometimes before they've even won the job, which reduces flexibility for changes as the project matures. Construction on the New Harbor Bridge project started in 2016 with an original completion date of 2020. But another bridge halfway across the country would soon throw the project into disarray. In March of 2018, a pedestrian bridge at Florida International University in Miami collapsed during construction, killing 6 people and injuring 10 more. After an extensive investigation, the National Transportation Safety Board put most of the blame for the bridge collapse on a miscalculation by the engineer, FIG, the same engineer hired by Flatiron and Dragados to design the New Harbor Bridge project in Texas. I should note that FIG disputes the NTSB's assessment and has released their own independent analysis pinning the blame for the incident on improper construction. Nevertheless, the FIU collapse led TxDOT to consider whether FIG was the right engineer for the job. In November of 2019, they asked the DB contractor to suspend design of the bridge so they could review the NTSB findings and conduct a safety review. And only a few months later, TxDOT issued a statement that they had requested their contractor to remove and replace FIG bridge engineers from the design of the main span bridge. That meant a new engineering firm would have to review the FIG designs, recertify all the engineering and calculations, and take responsibility for the project as the engineer of record. Later that year, FIG would be fired from another cable-stayed bridge project in Texas, and in 2021, they were debarred by the Federal Highway Administration from bidding on any projects until 2029. It took about 6 months for the New Harbor Bridge DB contractor to procure a new engineer for the main span. The contractor said it expected no major changes to the existing design. Construction on the project forged ahead through most of the shakeup, with steady progress on both of the approach bridges that lead to the main span. These are impressive structures themselves, with huge columns supporting each span above. The bridge superstructure consists of 2 rows of segmental box girders, massive elements that are precast from concrete at a site not far from the bridge. For each approach, these segments are lifted and held in place between the columns using an enormous self-propelled gantry crane. Once all the segments within a span are in place, steel cables called tendons are run through sleeves cast into the concrete and stressed using powerful hydraulic jacks. When the post-tensioned tendons are locked off, the span is then self-supporting, and the crane can be moved to the next set of columns. This segmental construction is an extremely efficient way to build bridges. It's used all over the world today, but it actually got its start right here in Corpus Christi. The JFK Memorial Causeway Bridge was replaced in 1973 to connect Corpus Christi to North Padre Island over the Laguna Madre. It was the first precast segmental bridge constructed in the US. And if you're curious, yes, qualified personnel can get inside the box girders. It's a convenient way to inspect the structural members to make sure the bridge is performing well over the long term. The Harbor Bridge project will include locked entryways to the box girders and even lights and power outlets within. Work on the main span bridge didn't resume until August of 2021, nearly 2 years after TxDOT first suspended the design of this part of the project. And by the end of 2021, both pylons were starting to take shape above the ground. Early this year, the contractor mobilized 2 colossal crawler cranes to join the tower cranes already set up at both the main span pylons. These crawlers were used to lift the table segments where the bridge superstructure connects to the approaches. The next step in construction is to begin lifting the precast box girder sections into place while crews continue building the pylons upward toward their final height. Rather than doing the entire span at once, these segments will be lifted into place using a balanced cantilever method, where each one is connected to the bridge from the pylon outward. But it probably won't happen anytime soon after TxDOT suspended construction on the main span in July and has continued a very public feud with the contractor since then that's far from resolved. During the shakeup with FIG, TxDOT hired their own bridge engineer to review the designs and inform their decision that ultimately ended with FIG fired from the project. When the DB contractor hired a new engineer to recertify the bridge designs, TxDOT kept their independent engineer to review the new designs. Unfortunately, many of the flaws identified in the FIG design persisted into the current design of the bridge. In April of 2022, TxDOT issued the contractor a notice of non-conforming work. This is a legal document in a construction project used to let a contractor know that something they built doesn't comply with the terms of the contract. And when that happens, it's the contractor's job to fix the non-conforming work at their own cost. The notice included the entire independent review report and a summary table of 23 issues that TxDOT said reflected breaches of the contract, and it required their contractor to submit a schedule detailing the plan to correct the non-conforming work. But they didn't provide that schedule, or at least not to TxDOT standards. So, in July, TxDOT sent another letter enacting a clause in the contract that lets them immediately suspend work in an emergency situation that could cause danger to people or property, citing 5 serious issues with the design of the main span. So let's take a look at them. The first 2 of the alleged flaws are related to the capacity of the foundation system that supports each of the 2 pylons. Each tower sits on top of an enormous concrete slab, or cap, that is the area of 2 basketball courts and 18 feet, or 5.5 meters thick. Below that slab are drilled shaft piles, each one about 10 feet or 3 meters in diameter and 210 feet or 64 meters deep. The most critical loads on the pylons are high winds that push the bridge and towers horizontally. You might not think that wind is powerful enough to affect a structure of this size, but don't forget that Corpus Christi is situated on the Gulf Coast and regularly subject to hurricane-force winds. The independent reviewer estimated that, under some loading conditions, many of the piles holding a single tower would be subject to demands of more than 20% of their capacity. In other words, they would fail. The primary design error identified in the analysis was that the original engineer had assumed that the pile cap, that concrete slab between the tower and the piles, was perfectly rigid in the calculations. All of engineering involves making simplifying assumptions during the design process. Structures are complicated, soils are variable, loading conditions are numerous. So, to make the process simpler, we neglect factors that aren't essential to the design. And with a pile cap that is greater in depth than most single-story buildings, you might think it's safe to assume that the concrete isn't going to flex much. But we're talking about extreme loads. When you take into account the flexibility of the pile cap, you find out that the stresses from the pylon aren't distributed to each pile evenly. Instead, some become overloaded, and you end up with a foundation that the design reviewer delicately labeled as exceedingly deficient to resist design loadings. The next critical design problem identified is related to the delta frame structures that transfer the weight of the bridge's superstructure into each cable stay. These delta frames connect to the box girders below the bridge deck using post-tension tendons. But these tendons can't be used to resist shear forces, those sliding forces between the girders and the delta frames. For those forces, according to the code, you need conventional steel reinforcement through this interface. Without it, a crack could develop and the interface could shear apart. The fourth issue identified is related to the bearings that transfer the weight of the bridge deck near each pylon. The independent reviewer found that under some load conditions, the superstructure could lift up rather than pushing down on the tower. That would not only cause issues with the bearings themselves, which need to be able to resist movement in some directions while allowing movement in others, it would also cause loads to redistribute, reducing the stiffness of the bridge that depends on a rigid connection to each tower. The final issue identified, and the most urgent, is related to the loads during construction of the bridge. Construction is a vulnerable time for a bridge like this, especially before the deck is connected between the pylons and the first piers of the approaches. The contractor's planning to lift derrick cranes onto the bridge deck that will be used to hoist the girder segments into place and attach them to each cable stay. TxDOT and their independent reviewer allege that the bridge isn't strong enough to withstand these forces during construction and will need additional support or more reinforcement. For the contractor's part, they have denied that there are design issues and issued a statement to the local paper saying that they were confident in the safety and durability of the bridge as designed. In their letter to TxDOT, they cite their disagreements with the conclusions of the independent design reviewer and accuse TxDOT of holding back the results of the review while allowing them to continue with construction and ignoring attempts to resolve the differences. Because of TxDOT's directive to suspend the work, they've already started demobilizing at the main span, reassigning crews, and reallocating resources. In August, TxDOT sent another letter notifying the contractor of a default in the contract and giving them 15 days to respond. It's hard to overstate the disruption of suspending work in this way. Construction projects of this scale are among the most complicated and interdependent things that humans do. They don't just start and stop on a dime. And these legal actions will have implications for thousands of people working on the new Harbor Bridge project. Just the daily rental fees of these 2 crawler cranes alone is probably in the tens of thousands of dollars per day. Add up all the equipment and labor on a job this size, and you can see that the stakes are incredibly high when interrupting an operation like this. It's never a good sign when the insurance company is CC'd on the letter. If the bridge design is truly flawed, and clearly TxDOT thinks that it is since they're sharing the evidence publicly, it's a good thing that they stop the work so the issues can be addressed before they turn into a dangerous situation for the public. But it also begs the question of why these concerns were handled in a way that let the contractor keep working even when TxDOT knew there were issues. Mega projects like this are immensely complex, and their design and construction rarely goes off without at least a few complications. There just isn't as much precedent for the engineering or construction. But we have processes in place to account for bumps in the road, and even bumps in the bridge deck. Those processes include thorough quality control on designs before construction starts. So who's at fault here? Is it the DB contractor for designing a bridge, then recertifying that design with a completely new engineering team that apparently had a number of serious flaws? Or is it TxDOT for failing to catch the alleged errors, or at least failing to stop the work until the very last minute after hundreds of millions of taxpayer dollars have already been spent on construction that may now have to be torn down and rebuilt? The simple answer is probably both, but it's a question that's far from settled, and the battle is sure to be dramatic for those who follow infrastructure, if not discouraging for those who pay taxes. The design issues are serious, but they're not insurmountable, and I think it's highly unlikely that TxDOT won't see the project to completion in one way or another. Some work may have to be replaced, while other parts of the project may be fine after retrofits. The best case scenario for everyone involved is for TxDOT to repair their relationship with the contractor and get the designs fixed instead of firing them and bringing on someone new. In the industry, they call that stepping into a dead man's shoes, and there won't be many companies jumping for a chance to take over this controversial job halfway through construction. Two things are for sure, as they almost always are in projects of this magnitude. The bridge is going to cost more than we expected, and it's going to take longer to build than the current estimated completion date in 2024. There's actually another, much longer cable-stayed bridge racing to finish construction in the US and Canada between Detroit, Michigan and Windsor, Ontario. Barring any major issues, it's currently scheduled to be complete by the end of 2024, and will probably now be the Corpus Christi project. Every single person who crosses over either one of those bridges, once they're complete, will do so as an act of trust in the engineers who designed them and the agencies who oversaw the projects. So I'm thankful that TxDOT is at least being relatively transparent about what's happening behind the scenes to make sure the new Harbor Bridge is safe when it's finished. As someone who lives in South Texas, I'm proud to have this project in my backyard, and I'm hopeful that these issues can be resolved without too much impact to the project's schedule or cost. The latest headlines make it seem like things are headed in that direction. Until then, if you're in Corpus Christi crossing the ship channel, as you drive over the aging but still striking and still standing Old Harbor Bridge, you'll have a really nice view of an impressive construction site and what was almost the nation's longest cable-stayed bridge. And if you want to learn more about the various kinds of bridges we use to cross waterways, or how to spot and identify the most interesting aspects of tunnels, dams, sewers, and the power grid, I have the book for you. I mean, I actually have it now. My new book, Engineering in Plain Sight, comes out this November, but I got an early copy in the mail just a few days ago, and I couldn't be more proud of how it came out. Engineering in Plain Sight is a field guide to the constructed world, full of colorful illustrations of all the things you might not notice in your built environment. When I was studying engineering in school, every class was like a lamp turning on to illuminate some innocuous part of my surroundings that I had never even paid attention to. Engineering in Plain Sight is my way to share that joy and help you further your journey as an enthusiastic beholder of the constructed environment. It's basically 50 new practical engineering episodes crammed between 2 covers. The book is available for pre-order pretty much anywhere you buy books and comes out on November 1st. If you want a signed copy for yourself or as a gift, I have them on my website at practical.engineering, and all pre-orders come with an exclusive enamel weir pin taken from one of the book's illustrations. I worked so hard on this project, and I'm so excited for you to see the final book. Thank you for watching, and let me know what you think.